Our next speaker is Adam Perlin, who is a software engineer at Microsoft Azure, and he's completed his bachelor's and master's at Cal Poly San Luis Obispo, with a master's thesis focused on what he's going to talk about today, which is incrementally developing support for Racket-to-Wasm compilation. And I'm pretty sure it's going to be a pretty Wasm talk, so give it up to Adam. For Adam.
Okay, great. So the microphone appears to be working. Folks can hear me okay? Awesome. So I truly don't think I can... Oh, okay. Well, unexpected things happen. Yeah. All right, that seems to be okay. But yeah, I truly don't think I can top that pun there. So apologies for that. But yeah, let's get rolling here. Okay, so as was mentioned, yeah, I'm going to be talking a bit about Racket-to-Wasm compilation. This is a thesis that I completed for my master's degree at Cal Poly San Luis Obispo under John Clements, who is here in the audience today, with some guiding ideas from Matthew Flatt, who is also in the audience today. So let's talk about where we're going to go here in terms of agenda. I'm first going to give you just a tiny bit of Wasm background in case you're unfamiliar. Is anyone here familiar with Wasm, by the way? Oh, yay. Okay, good. Okay, so maybe a little less on that. How this idea for Racket-to-Wasm conversion works, like obviously, like what are the technical details here? How well does it work? So I'm gonna present just some initial sort of benchmarking results, and then next steps, because that's a major goal of this talk is if handing this over to the community in terms of if people are interested in continuing along this line of research. It's not something that I'm actively working on anymore. So let's get started with a bit of Wasm background. Okay, so Wasm it's the executable format for a stack-based virtual machine, which means that it is platform independent. Its semantics are formally specified. It is sandboxed, and by that I mean that the memory is isolated to within a module. It's relatively simple, and by that I mean you can fit the grammar for at least, this is a slightly older version of Wasm, but on this, just in this figure here. So again, that's pretty small if you think about it in terms of an instruction set. And it's widely supported in all major browser implementations now. It was actually designed to be added in a fairly straightforward way on top of existing JavaScript engines. And there are some poster children for Wasm, like AutoCAD. AutoCAD is like a web version that makes use of Wasm, as well as Figma, the graphic design tool. So a lot of projects that are using Wasm. And I should mention as well that there's also a possibility for use of Wasm in contexts beyond the browser, for instance, like as a cloud runtime, which is pretty exciting work as well. So it's this platform that has this increasing adoption, and that makes it a pretty interesting compiler target, which is not yet supported under Racket fully. So what does Wasm look like? Now, this is very important to understand because some of the restrictions that are present in the semantics of Wasm make it a little more challenging as a compiler target. So this is kind of a super canonical factorial example where it's just like an iterative multiplication in a loop. But what I want to bring your attention to here is the nesting of the blocks. So you can see we have an outer block which wraps a loop. And the reason that the outer block is there is because we need a place to break to. You can think of control flow in Wasm as sort of like pushing blocks onto a control stack. And in order to jump to a point, you have to essentially unwind the control stack, which means that that block had to already be there in the first place. This isn't an exact analog, but to sort of get your mind thinking in the right direction. It's a little bit like if in an assembly language you could only do like breaks and continues to labels. So it's actually quite different. The reason for it being this way is to make the control flow graphs for Wasm reducible, which speeds up verification of Wasm, but of Wasm source, but it doesn't make things any easier on the compiler side. Especially in Racket, which I'm going to get to in just a second here, the Racket CS compilation pipeline. So Racket CS is the implementation that probably most folks are using. That's the implementation of Racket that uses Chez Scheme, which is a native Scheme compiler, originally developed by Kent Dybvig. Uses Chez Scheme as its native code generation backend. And there was a big push a few years ago to make that switch over. So what does the Racket CS compilation pipeline look like? Well, it looks something like this. So you start with Racket source, which has all of the meta-programming features and macros that we know and love. And of course, that all has to be expanded away by the expander into just core Racket. And the output of that, the output of the expander is going to be these fully expanded linklets, which are these independent compilation units that only consist of the Racket core forms. Now, because of the Chez Scheme backend, right, Chez Scheme is a scheme compiler. There are some differences between scheme is specified and Racket, and so the schemify pass takes care of that, and then we're at the Chez Scheme level. And Chez Scheme is a rather interestingly architected compiler because it uses what's called a nanopass framework, which is not too common. And the idea here is to break the relatively complicated work of compilation to a bunch of passes, like a lot, like 50 of them. And so each pass does a tiny little bit of work, actually lowering all the way down from the first pass, which is operating on scheme source, down to machine code. And so each of these passes you can think of at a high level as sort of like functions from an intermediate language to another intermediate language. And so as you walk through the passes, right, each pass is consuming an intermediate language, doing some transformations, outputting an intermediate language. Sometimes the same intermediate language, sometimes a different one. And we get all the way down to the last level and sort of like the back end of the back end, so to speak. And that's actually going to be doing the instruction selection. And that's structured as an interface, because you can see at the bottom of this diagram here, Chez Scheme is retargetable in that it supports multiple different ISAs, including ARM, x86, et cetera. And so this backend interface, it consumes a very, very low-level IL, and then it produces selected instructions for that IL. But the key thing here, right, is that it's an interface, and it's assuming certain capabilities for the ISA that it's targeting. And this very low-level IL that's being consumed uses a lot of unstructured branching. Just jumps to memory addresses or loading from a place and then jumping to it. And the reason for this would get complicated, but the reason for this is because of some of the interesting control features of Scheme, such as first-class continuations, support for proper tail calls, right? It's easier to just lower everything to jumps and then do the appropriate stack manipulations or lack thereof. So that's kind of why it's implemented that way. It makes our life harder at the back end because it means, okay, well, if we want to then target an ISA that doesn't support unstructured jumps very well, we're then consuming an IL with tons of unstructured jumps everywhere. How do we deal with that? And so that's where this Racket-to-Wasm comes in here. It's kind of hard to just slot Wasm in. Actually, very difficult, in fact, just slot Wasm in as another backend. So that's the context for all of this work, is it's hard to make a backend for Chez Scheme. But this is where PB comes in. So what is PB, you ask? Well, PB is an alternate ISA, which is supported by the backend of Chez Scheme. It was created by Matthew Flatt for making it easier to port Chez Scheme to new platforms. Not the most needed context, but that's what it's there for. So yeah, PB is an interpreted bytecode. And so it has an associated interpreter. It's actually written in C. And the runtime system for Chez Scheme, which includes like the GC and runtime libraries, like all of that stuff, is also written in C. So you can kind of think of the PB interpreter as sort of living in that Chez Scheme kernel. And what's really nice about this is it's C, and Incrementally exists. And Incrementally is an LLVM to Wasm compiler. It fits into the LLVM toolchain. It can compile C to WebAssembly. Great. So to give you just a sense of what PB looks like, as I feel like I kind of need to here, here's a simple max function in Scheme, and I'm going to just show you like the first sort of like a fragment of instructions. And this output actually comes from a disassembler for PB that I wrote as part of my debugging process. It doesn't really matter that much what this is doing. This is actually doing an argument count check and some type checking to dispatch to different points in the function. Really, all this is to say that PB is a more standard kind of ISA. It kind of looks a bit like ARM. It's a RISC sort of thing, and it has unstructured branching. So like a backend for Chez Scheme, it exists. We can compile Racket on top of PB and run it in the PB interpreter. And that's really nice, because what then that allows us to do is do PB on top of Wasm, and then by extension support Chez Scheme and Racket on top of Wasm by simply compiling the kernel of Chez Scheme with Incrementally to Wasm. And so on the face of it, it's like, okay, this kind of looks like a solution to our issue. I mean, I should note, like, this is a full installation of Racket that runs on Wasm. A little asterisk there. There might be a few things that don't work properly, but more or less, yeah, like the GC is supported, like everything kind of just works. But there's a lot of layers of indirection here, and it's not necessarily like the fastest solution in the world. And it's also not really moving us that much closer to, like, hey, we want to actually be generating like native Wasm, because we're like really heavily relying on Emscripten here. So how can we improve this? Well, this is where pbchunk comes in. So pbchunk was developed by Matthew Flatt, and the idea here was to extract C chunk functions from compiled PB in this sort of ahead of time fashion. So you go through the compiled PB, and you select ranges of instructions, and then you translate those instructions into equivalent C code that essentially does what the interpreter would do to execute those instructions. And you have to register those chunks with the interpreter, right? So the interpreter knows that those chunks exist. And then you link everything together, and at runtime, when the interpreter is executing, it knows where the chunks are that's been annotated in the PB program. And then when it hits one of those instructions, it's the start of a chunk, it jumps into the chunk function and executes that instead of executing those instructions one by one. And so what that does is that eliminates a dispatch overhead of the interpreter having to figure out what to do when it reads an instruction. And so that can actually lead to significant performance gains. And so we can adapt this idea to Wasm directly, pretty much, with, surprise, Wasm PB chunk. So the idea here is, again, instead of, we're reusing the PB chunk approach, but instead of generating C, we're generating like Wasm directly. And that's, again, Wasm that's doing what the PB interpreter would do to execute those instructions. So we get those Wasm chunks, and then we can feed everything into Emscripten, so we can link those Wasm chunks with the PB interpreter, the schema kernel, et cetera, and just get a scheme.wasm out. And so that's essentially a version of Scheme that has an interpreter that is specialized to run a particular Scheme program. And again, this is using PB as sort of this intermediary. Okay, so that is kind of high level. So like, what do these chunks actually look like? A chunk consumes the state of the interpreter, right? Because when you are you need to bookkeep as you execute a chunk, because you're going to eventually jump back to the interpreter, at which point the state that changed during the execution of the chunk still needs to be there, right? And so you need to take in the machine state when you start executing a chunk, so that those changes, you can modify it, and those changes can persist. So yeah, these chunks are stub functions that take in machine state. And we do a trampolining sort of system where when we return back the address of the next instruction that the interpreter should execute. And this is really nice because we as the implementers of Wasm PB chunk, control what the chunk selection looks like what is actually going into chunks. And so right now, for my implementation, it's just using basic blocks. So we're essentially not doing branching in Wasm. And we can do that because we can essentially chunk a basic block and then return back to the interpreter to actually do whatever the branch is. So we're essentially returning the address that we want to branch to just back to the interpreter. And this kind of circumvents our branching problem for the time being, and that's really nice. So to make this even more concrete, right? This is a single PB instruction that's just an equality check of a register with the value 1. This is what the source code of the interpreter looks like, where, again, we're loading it out of a virtual register array and comparing it with the immediate value. And then there's a lot of generated Wasm, and again, a lot of this boilerplate comes from, we have to modify the interpreter state. We have to load the value out of the virtual register array, right, and then do the operation, which doesn't take that much Wasm, and then potentially store it back depending on what the operation is, and that again is a lot of boilerplate. So this seems like a lot, but when you consider that it's doing like memory accesses and things, it becomes a little more reasonable. So yeah, how well does this actually work? You might be wondering, like, how well does this perform? For my thesis, at least, I tested Wasm PB chunk using the Gabriel benchmarks, which come from the Larceny project. And these benchmarks were kind of collected by Richard Gabriel, who's kind of known in the Lisp world. And it's a set of benchmarks that stress test various aspects of Scheme programs, including some fairly unique features like first-class continuations and things like that. And yeah, we do see some performance gains from doing this chunking. So if I direct your attention to the leftmost column here, we see speedups of almost like 1.65 times in the best case between Wasm on PB with chunking and Wasm on PB without chunking, which is like, you know, respectable. I'm gonna ignore the middle column for now and direct your attention to the rightmost column, which is just Wasm on PB, or sorry, PB on top of Wasm with chunking enabled as compared to just like native Racket like on x86. And surprisingly, like we don't do that poorly. I mean, at best we're actually at like almost 75% of native, and at worst we're maybe like 17% of native, which is not as bad as I was expecting. So it's, I guess suffice to say that this approach, like performance doesn't seem to be like a death knell for this approach, and it seems worthwhile to maybe investigate further, which leads me to sort of the next steps here. You know, what comes next with a system like this? Where could we go with it? So yeah, the build process right now for doing this is like a bit of a nightmare. It's one reason why I'm like not gonna live demo this. Because from Chez Scheme, you have to have, first of all, you already have to have an installation of Chez Scheme that targets PB. That's the first step. Then you compile your scheme file. You have to actually make it into a boot file as well. That's not too bad. That could be automated. And then you have to chunk the file. And that's sort of the script that I created. And then this is the annoying part, right? You have to essentially rebuild the kernel of Chez Scheme for every program that you want to execute. And that's where things get annoying, because you don't want to have to like recompile your compiler for every program that you want to execute. It's not the most convenient. So what would we want in an ideal world? Well, ideally, you can have this scheme on PB on Wasm built as sort of the standalone thing. And then scheme programs can be compiled and chunked to Wasm just like in an on-the-fly sort of way, and that could potentially, I mean, potentially even thinking about like interactive compilation, which would be really, really cool. And another sort of smaller step here too would just be even just like, even for getting like interactive compilation, just not having to relink every time you want to run a new program would be really nice. Like if you didn't even have to have Mscripted installed to do the relinking and the recompilation, that would be really cool. Some of this is complicated by the Wasm memory model, where it's kind of against in its philosophy, just sort of like, oh, like here's some new code that got created at runtime. Like let's put it in the memory space and run it. Like that's not really the Wasm philosophy on running programs. And so I'm not going to say this is impossible, but it's just that might complicate things. So that's something to keep in mind. Another improvement would be, so I mentioned earlier that we're only chunking basic blocks right now because of this. We're using this sort of trampoline-based system. And so it'd be really nice to support localized branching. And by localized branching, I mean like branches within the confines of a function. Calls are a little bit more complicated, and that could be a harder problem to support natively in Wasm. So the basic idea here is that we're entering and exiting these chunks. And if you increase the chunk size, that's going to help amortize the cost of doing those entrances and exits. But yeah, chunks are combined to basic blocks. And so one solution to this would be to apply some of Mscripton's approach to this problem, relooper. And the idea behind relooper is to do a transformation on a control flow graph and generate a proper nesting of blocks. They're put in a loop, and there's like a variable that you set to like figure out what next block you want to jump to. But essentially, this transformation is meant to mimic a sort of arbitrary branching structure within the confines of Wasm. And so that transformation would need to be done on like generated PB chunks or Wasm chunks if this were to work. So there are some complications there. But it's nice because we can think about like if chunks could encompass like entire functions, which they certainly can't now, then again, that would do more to like amortize the cost, and that would potentially pave the way for like getting closer and closer to like doing more and more stuff just in Wasm, using the interpreter less and less. And that's really exciting from a performance standpoint. So conclusions here, and we are, oh, okay, we're doing okay in terms of time. The last thing I want to do here is keep you all from lunch, because that's about to happen. So this approach does provide kind of an alternative path to Racket-to-Wasm. Like there is other work going on in the kind of Scheme community at large. Like Andy Wingo has done a lot of work on like getting Guile to compile the WebAssembly, and like that's using an almost like completely different approach here, which I don't know if people would have questions about that, but basically the idea here is this is kind of an ultimate path by like going at the problem at like a very low level, where it's like, hey, we already are compiling this low level bytecode, well, let's use the interpreter, compile out some script, and like do this interpreter chunking to speed things up. And so that allows for this feature completeness. We don't have to go back and re-implement a lot of the complexities of the Chez Scheme system in Wasm, because it's we kind of already get that, because it's already working on top of PB. And yeah, we don't need to do backend interface modification. There might well be a way to make a backend that works for Chez Scheme, but it's proven pretty elusive so far, and this sort of avoids that. And yeah, this final point here is an important one, right? This is just like a very small kind of first step. A lot more work would be needed to make this actually practical, to drive the idea forward. So if people are interested in taking anything related to this on, I do have a fork of Racket that has my work for this in it. It is a proof of concept. I'm going to try and license it under the Crapple academic license to the extent that I can. Because again, proof of concept, don't expect it to do too much, but it's there. Yeah, thank you. We have, I guess, the rest of the time for questions. And I have a reference. That's the Wasm diagram of the Wasm grammar. Yep.
All right, we have a question from the live stream audience.
Oh yeah, what's the question?
And the question is, thanks for this very exciting work. In the thesis, you note that Wasm PB configuration greatly outperformed native PB configuration.
Yeah.
Did you try a native PB chunk configuration?
Yeah. Did I try a native PB chunk, like using PB chunk and then using Wasm on those like generated C chunks? Or are you talking about the second column over in the table?
It doesn't clarify that, but I think.
Wait, sorry, can you just read the question again?
Yeah, the question says, in your thesis,
yes,
you note that Wasm PB configuration greatly outperformed native PB configuration.
Oh, okay, sorry, yes, that is the second column. Yeah, okay, this is the weird one. This is the weird column. Okay. I didn't, I was expecting someone to mention something based on that. Yeah. Okay, so yeah, you see these massive speedups in the second column. And yes, this is the Wasm PB configuration versus the native PB configuration. That is the PB interpreter, Chez Scheme kernel compiled for Wasm versus native compilation. I ran into this result as I was doing testing, and it was quite frankly pretty bizarre to me. I don't know what the reason for it is. One possible reason is that my native compilation configuration for PB was like really bad. And like I messed something up or omitted some optimization flag that I should have. Another possibility is that the Wasm JIT is able to greatly optimize the interpreter loop for PB based on just like potentially on the fly performance profiling or some optimization that it's doing, and that's giving the massive speedups. Because you can think about the interpreter loop, right? That's an incredibly hot section of code that's being executed again and again. So you have a really good JIT that could potentially account for pretty big performance gains.
Okay, so that's actually the next question. What runtime is used to interpret the Wasm? Does it JIT and hot code optimizations? And it sounds like the answer.
Yeah, so that was Turbofan, or the Turbofan, V8 Turbofan. Yeah, I don't remember the exact version, but yeah.
Thanks for a really cool project and talk. I'm Sam Tubman-Hochstadt.
Yeah.
So would it be possible to just adapt this to use the new garbage collection features in Wasm? Or is the Chez garbage collector sort of built more deeply in so that it would be hard? Or have you looked at that at all?
Yeah, that was another question I was definitely expecting to get. So from my understanding, kind of the point of this was to almost avoid that and just use what we have currently, because yeah, it is pretty tightly coupled, because it's almost like like all of that's almost already been dealt with, like at the PB layer, and then we're just sort of doing the additional step of translating the PB layer. So that would likely require a pretty different compilation approach to take advantage of some of the new Wasm features like the GC. Like Wasm is getting like tail call support. Wasm is now getting these features that are like making it easier for functional languages to target it. And that's just kind of a hard thing about targeting Wasm, because it's kind of this like moving target of like there's a lot of innovation going on in the space right now. So I know Andy Wingo's work for Guile like is doing that, like is making use of the new GC proposal and tail calls and that kind of stuff. Yeah.
Hello, my name is Jeremy Seek, and this was a great talk, a lot of fun to learn about what you're doing. Just a question about sort of the design space of where you're going and sort of alternatives. I was thinking that one possibility would be to, instead of waiting till past 50, to branch off higher up somewhere, 40 or 45 over to Wasm. And so the question is, have you considered that? Is that what you were kind of referring to a moment ago? I'm not sure in terms of alternatimes.
Actually, yeah, a little bit.
And are there reasons why that's like difficult or not as good or something?
I mean, difficult. I think it would be difficult. And this was something that actually a previous master's student of John Clements explored, is like, where would that branching off point be, that would be appropriate for Wasm? And I think the downsides there are mostly like, you're kind of forking off the compilation pipeline, and now you have this new pipeline that's like only for Wasm that you have to maintain. And so I think along those lines, it's more of it almost becomes like, it would be a ton of work to do. It would be a hard problem in terms of like doing those, like you'd be redoing some of the work maybe that the compiler is already doing in its main pipeline over in Wasm world. And it is kind of a software engineering problem of, now you have this like separate, if the work were to be done, then you'd have this big separate like compilation pipeline that would, just for Wasm, that have to be maintained. But like, it could be a very viable approach. And that might be the direction that we need to go moving forward. But does that answer your question? Or?
Oh,
yeah, okay.
Thanks.
Another question from the live stream audience. Does the Wasm spec do proper tail recursion yet?
So there was a proposal. I think it was accepted. In some version of Wasm, yes. I don't know what spec it's in. I think it's in some spec somewhere, and I think some engines are already implementing it, but I don't know like how standardized it is and like how wide the support is.
One of the things that a lot of Racket programs use is GUIs.
Mm-hmm.
Like I see you running a Racket program here that's
Yeah.
using a GUI, for example. So I wonder if you have any thought about how that would integrate, or what would be the right way to plug it in with.
Yeah. To be honest, I wouldn't feel too comfortable speaking on that, just because it's really not something that I looked into so much. There's a lot of interesting avenues to think about in terms of if you can run like Racket code in the browser, and like how could you take advantage of like browser like rendering capabilities and things like that. So I guess that's the extent of it that I would say, but there's that's not really something I looked into too much. This is pretty just like very back-end like focused. Yeah. Any other questions or?
All right. Thank you, Adam.